could be of different sizes, m and n, and we want to return the median of both of the arrays when they have been put together and sorted. So not individually, but we want to put them together and then find the median of both of them. And not only that, but we want to do it efficiently. So log of m plus n worst case, right? So one example, we can see one array could be 1, 3, another array could be 2. And in this case, when you put the two arrays together, it's pretty obvious that 2 is the median, that the median is the middle value. Now we know that there are other examples where we might have an even number of total elements, 1, 2, 3, 4. When you put those together, we get 1, 2, 3, 4. In this case, we have two numbers that are in the middle, 2 and 3. So what do? We can just take the average of these two. And we know the average is 2.5. But both of these examples used a merged array. But we know if we actually merge two arrays together, like 1, 2, and 3, 4, the worst case is actually big O n plus m. And that's not log. So we know in most cases, when people want a log algorithm, you need binary search, and that's exactly what I'm going to show you right now, how to solve this problem with binary search. So let's say we are given a different example. Let's call this array B, and let's call this array A. So we know we can merge these two arrays, right? And then the median is obvious. But what exactly is a median? Well, it's the middle value, right? In this case, this is the middle value, and we know that because we know to the left of it, there are 6 elements, and to the right of it, there are 6 elements. So in this case, we have an array of 13 elements, and this happens to be the middle. The left partition of 6 elements is the same size as the right partition of 6 elements. So what we're doing is partitioning the array into 2 equal halves roughly, right? Because we know there's an odd case and an even case. Now let's just take hypothetically this 8 doesn't exist. Then in reality we have 12 elements. So we take the left partition to be 6 elements and the right partition to be 6 elements. So in that case we know we can take the two middlemost elements, or in other words, the rightmost value in our left partition and the leftmost value in our right partition and take the average. So add them together and divide by 2. We know that's going to be 3.5. So how can we simulate that without actually merging these two arrays? How can we simulate that with just the original arrays, which are still in sorted order, right? Luckily for us, they are given in sorted order. So keep in mind that the total number of elements we have in this case is 13, and half the number of elements we have is roughly 6. I'm going to round down in this case. And when we talk about partitioning, we want our left partition to be roughly equal to half. So when we partition this, we want the left to be roughly 6. So the most intuitive way to do this is, let's get half of the elements of, let's say, A, right? So I'm going to have a left pointer initialized here, and I'm going to have a right pointer initialized here, and I'm going to find the middle. So we know this is index 0, this is index 4. I add them together and average. So we know that the middle is going to be 2, right? So what are we actually going to do? So this is going to be our middle value, right? And basically what that means is our left partition is going to include that. So far, our left partition initially is going to be like this. Now, obviously, we can increase it by adding an element. We can also decrease it by removing an element. But initially, let's have our left partition have 3 values in it. So it has 3 values, great. Now can we repeat that same process up here? Well, the good thing is we don't actually need to, because look, in this case, if we do that, we're gonna get 4, and we can basically, if we want, we can run binary search up here too, but is that even necessary? Because look at this, half our elements are 6. So really what we can do is say half minus 3 over here is going to be equal to 3. So if we run binary search on just this bottom array, we can compute the size of the left partition for the second array, right? We can just compute it using our half value. And since we know 6 minus 3 is 3, we know initially we can say that the left partition of this is going to be 3 as well. We don't even need to keep a left and right pointer for this array. So these two subarrays make up our left partition. Now my question is, how do we know if we found the correct left partition or not? Well, we want them to be in order, right? So notice how we already know that this 3 is going to be less than or equal to the element that comes after it. That's what sorted order means. And we already know this value is going to be less than or equal to the value to the right of it, because this is also in sorted order. But we want to make sure that the left partition is less than or equal to every element in the right partition, and this is our right partition. So how can we determine that? Well, one thing we can ask is the rightmost element in this part of the partition less than or equal to this value? And in this case it is. We also want to ask, is this value less than or equal to the leftmost value in this part of the partition, in the right partition? Is it less than or equal to that? In this case, it is. And what this tells us is that our left partition has been done correctly. And if it's not clear enough, let me just write it out again. So remember, if we merge these two arrays, this is what it's going to look like. And our left partition is going to be this, right? We have 13 elements. This is our left partition. And we can say that this is our right partition, but since it's odd, we can add that extra element. And you can see that that's exactly what we found here, right? Okay, so we know we found the left partition correctly, right? So the left is going to be this 6 element, but how do we find that middle value? Well, in this case, either of these two is a 4, so either of them is going to be the median, right? We have 2 4s, either of them could be the median. But hypothetically, let's say one of these was a 5, so let's say maybe in the top we had a 5, so this would be a 5. How would we find the median in that case? Well, from these two values, right, we know one of them has to be the median. What we would do is take the minimum of both of them. So we'd take the minimum of the leftmost values in both partitions. So the min of 5 and 4. And we know that's going to be 4, so 4 is our median. So this example was a little too easy because we didn't actually really need to run a search. So let's remove one element and let's update our total to 12 now instead of 13 because we just removed one. The half is still going to be 6. So now let's do the same thing. Our right pointer is going to be here. This is index 0. This is index 3. We divide 3 by 2. We're going to round down to 1. So this is going to be our middle position. And what that tells us is our left partition is going to be like this. And now how do we get the left partition of this? Well, similarly, we can take 6 minus 2, which is the size of our left partition. So we get 4. So the left partition of this is going to be of size 4. We take the first 4 elements. So now let's check. Do we have our left partition correctly? Have we done it correctly? How can we check that? Well, let's check that this 2 is less than or equal to the 5. We know that's true, right? 2 is less than 5. What about this value? Is the rightmost value in this partition less than or equal to this? It's not, right? 4 is not less than or equal to 3. That's just not true. So our left partition is not correct in this case, right? How can our left partition have a 4 where our right partition has a 3? That means we have not partitioned it correctly. So what that tells us is we have to update these pointers, right? Because we are doing binary search. So initially our left or our middle was over here. So what we're going to do is take our left pointer and then shift it 1 plus the middle value, the old middle value, because we know that we're going to need extra elements from array A. So with our left shifted over here, we're going to recompute the middle. We know the index of this is 2, this is 3. We add them together. 2 plus 3 divided by 2. If we round down is going to be 2. So what's going to end up happening is our left partition is now going to be these 3 elements because mid is going to be over here. And so how many elements from our array B are we going to need? Well, let's just compute it, right? Half is 6 minus 3, because that's the size of this partition, is going to total to be 3. So we know that the partition from B is also going to need to be size 3. So let's get the first 3 elements of this. Now let's check, have we partitioned our left, have we partitioned this correctly? So let's check, is this 3 less than or equal to this value? Yes, it is. 3 is less than 4. Is this 3 less than or equal to this value? Yes, 3 is less than or equal to 4. So that tells us we finally partitioned our arrays correctly. But you saw originally we had 13 elements, so it was odd. And when it's odd in that case, what we had to do was take the minimum of these 2 values, right? But in this case, it's even. So what are we actually going to do now? So how are we going to find the median? Well, how would we do it if we had a sorted array? So this is how the sorted array would look if we merged these 2, right? And we can see that, look at our left partition. We have 1, 2, and 3, right? So this is our left partition right now, right? It's size 6. This is our right partition. It's also size 6. So clearly, if we actually want to find the median, what we have to do is take the max value from our left partition and take the minimum value from our right partition, right? Like that's pretty obvious. So how do we translate that when we actually have 2 separate arrays? How do we actually translate that? Let me show you. Well, we can take the minimum of these 2 values, right? And in this case, they're clearly the same, but if they were different, we would want to take the minimum of both of them, right? And we would want to take the max of these 2 values, of that and this, right? In this case, they're also the same, but they could be different hypothetically. So we would take that, right? And that's going to get us the 2 values we need to compute the median. And of course, we can just divide them by 2. So this is the main idea of this algorithm. You can see that it's actually somewhat intuitive once you understand some of the basic ideas. Let me just show you one last thing that's going to make the code a lot easier for us. Hypothetically, our left partition from this array, right, A, hypothetically it could be 1, it could also be 0, right? We want our left partition to be 6 elements. What if we just took the 6 elements from over here? That's going to make edge cases a little annoying. Like, you know how we always want to make sure that the value from over here is less than or equal to that, and we want to make sure that this is going to be less than or equal to something like this. But if we had 0 values here, I'm going to basically default that like there's a positive infinity over here and there's a negative infinity over here, so that if we wanted all elements to come from a single array, we would actually be checking, okay, is this less than or equal to the positive infinity? And I'm going to show you basically what I mean in the code, but I hope that the main idea of what we're doing, the binary search to find the median, is at least somewhat obvious now. So we have 2...
Okay, no code, no code. I'm not checking the code. Holy shit. So, so first, so I want to do it. Fine. 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 How? Rich earning. We also get the so color.
arrays, nums1 and nums2, I'm going to assign them to different variables. We'll call them A and B. And you know how we only have to run binary search on one of them, I'm going to make sure that we run binary search on A, and I'm going to make sure that A is the smaller of these two arrays. So we'll check if the length of A is bigger than B, then we're gonna swap these two arrays. We're gonna swap A and B. So let's also get the total and half length of each of these. So the total is just gonna be the length of each added together, and half is just gonna be total divided by 2. In Python, we need the double if we want to do integer division. So now I'm going to run binary search on A because A is the smaller, so the left and right pointers are going to be 0 and length of A minus 1. And remember that half is going to tell us the total elements in the left partition. So now I'm just going to be lazy and say while true, we're going to start looping. We're going to run our binary search because we know that there's guaranteed a minimum. So once we, or there's guaranteed a median. So once we find it, we can just return it. So now, of course, we want to compute the middle value of array A that we're going to use to get our left partition. So we're going to take left and right pointers, add them together, divide by 2. Now, how do we get the, and so this is referring to A, so we'll call this is for A. This is the pointer for B. Now, we don't actually need to divide anything by 2. We can just take half and subtract I from it. But one thing you need to know that this is going to be the index. So to get rid of the off by 1 errors, J is not actually the number of elements in array B, it's actually the index of the midpoint. So we're going to take subtract I, and we're also going to subtract 2 from it because we know arrays are indexed at 0. And we're doing this because we know J starts at 0 and I starts at 0, so we got to do the extra minus by 2. So now we want to get the values, right? The values that we're actually going to need to compare to determine if we actually found the median, right? If we actually have a correct left partition. So, you know, we can take A left to be A of index I, right? That's going to be the value in the left partition that we're going to need to use to compare. And there's also going to be a value in the right partition of A, right? And we know it's adjacent, right? So what we can do is just take I plus 1. And we can repeat.
And
need to compute 3 because 4, we take the first 4 elements. So now let's check. Do we have our left partition correctly? Have we done it correctly? How can that mean? That's 0. And we're doing this because we know j starts at 0 and I starts at 0, so we got to do the extra minus by 2. So now we want to get the values, right? The values that we're actually going to need to compare to determine if we actually found the median, right? If we actually have a correct left partition. So, we can take a left to be a of index I, right? That's going to be the value in the left partition that we're going to need to use to compare. And there's also going to be a value in the right partition of A, right? And we know it's adjacent, right? So what we can do is just take I plus 1. And we can repeat this with B, right? So B left is going to be B at index J. B right is going to be B at index J plus 1. But here's the part where I'm going to make our lives a lot easier and avoid some edge cases. Now, any of these indices technically could be out of bounds, right? Isn't that true? So if I is out of bounds, hypothetically, what would that mean? That would mean I is less than 0. So if I is less than 0, is there a default value that we can give to A left? There is, and it's called negative infinity, right? So it's going to be set to A of I if I is greater than or equal to 0. So if I is still in bounds, set it to the value at this position. If it's not, let's default. The default value we can give this is negative infinity. And we can do the exact same thing for this one. If this j is actually out of bounds, it's going to be that j is less than or equal, is basically less than 0. So it's gone too far to the left. So if j is greater than or equal to 0, leave it as it is. Otherwise, set this to negative infinity. And what about this value? If I plus 1 is out of bounds, that must mean we want all the values in array A to be a part of our left partition. So if I plus 1 is out of bounds, the default value, that means that the default value we want to give it is infinity, because we've gone too far to the right. And otherwise, if I is less than length of A, then we will leave it as it is. Or I plus 1 rather, right? We're checking if I plus 1 is out of bounds. And we're going to do the exact same thing for B. So if J plus 1 is within bounds, we can leave it as it is, get B of J plus 1. Otherwise, we're going to set it to positive infinity. So now finally with these, you'll see that we've actually just done the algorithm. Now our
Nope, I don't need an answer. So this can be need to do this. I'll also have all the the
Hey, less than length of
no one are not allowed to chat. So it's suppressed. I can't stop like a friend.
Correct left partition. So, and it's called negative infinity, right? So it's going to be set to a of I if I is greater than or equal to 0. So if I is still in bounds, set it to the value at this position. If it's not this value, and we're going to do the exact done the algorithm. Now our life is so easy. We can check if a left is less than or equal to b right, because
What? Man,
that's what we were doing in the picture, right? If that's true, and if b left is less than or equal to a right, that means our left partition is correct. So we found the median, but remember there's two cases. There's one case that we have an odd number of elements. So how do we know if we have an odd number? We can take the total number, mod it by 2. If this equals 1, then we have to compute the median odd. So if you remember from the picture, we can get that by taking the minimum of a right
that's odd.
and b right. We can take the minimum of these two
Here. Huh?
values and
I think they're really hot here. What? If A rate is I don't need task.
return it. Notice how if one of these values is an actual real number, let's say 4, and one of them is positive infinity, we're going to take the minimum of these two, so we're going to end up returning 4. Now, both of these will never be infinity. You can run through some examples to prove that to yourself. And if it's not odd, that means it's even length. So how can we get the median in that case? Well, we take
Oh,
the max of A left and B left, just like we did in the picture. We add that to the minimum of A right and B right.
oh,
So these are going to be the two values in the middle, and we can divide them by 2. We want decimal division in this case, and then we can return that value. So now in the case that we don't find the median, it could be possible that A left is greater than B right. Like that's a possibility, right? And in that case, basically that tells us that A left is too big. So we have too many elements from A. So we're going to reduce the size of A. So what we can do is take our right pointer and shift it to I minus 1. So we're reducing the size of the left partition from A. And the third case is just the else case, where it would be that this condition was not true. In that case, we would need to increase the size of our left partition from A. So we would say left is equal to I plus 1. And that's actually the entire code. So we don't need a return statement outside because we know that our loop is eventually going to find a median and we're going to return it whether it's odd or whether it's even. So you can see we did this in about 30 lines of code, and it would probably be less if I removed some of the spaces in the comments. And the time complexity is basically going to be log of the minimum of n or m, because we're running binary search on the smaller of the two. And as you can see, it's a pretty efficient solution. And I really hope that this was helpful to understand like the big picture. It's a difficult problem. I probably wouldn't be able to figure this out on my own, but you can see it is definitely understandable once you know some of the tricks behind it. Don't forget to like and subscribe if this was helpful. It supports the channel a lot, and I'll hopefully see you pretty soon.